Okay, I want to talk about batch melting or crystallization. Uh, Same thing as equilibrium melting. We've already talked about this before, but what I want to do is talk about the case when you have an accessory phase that plays an outsized role on the geochemical evolution of some trace element. Let me give you an example. Consider the element zirconium. It's usually in trace levels in magmatic systems, so uh, it doesn't usually saturate and make a phase. But when it reaches some critical level in a magma, say about a few hundred parts per million, it's enough to actually form zircon. And we call this an accessory phase because, well, if you only have a few hundred parts per million, well, you aren't going to make a lot of zircon, but you will have it, just tiny, tiny amounts of it. So zircon is an example. And the key here is that in that mineral zircon, zirconium is an essential structural element. And there are some trace elements that are so strongly compatible in zircon that when zircon is present, it controls, even though there's not much of the zircon, it controls the behavior of that element. Examples might be hafnium, the rare earth elements. Okay, when zircon is not around and is controlled by all the other dominant phases, which typically are the silicate minerals. Another example, which I am very fond of, are sulfides, right? And sulfides might be something like this. Iron nickel solid solution sulfide. This would be a monosulfide solid solution, which you might find in the prototitic mantle, or it might be FeS, pyrrhotite, that would precipitate out of a magma, but only when your sulfur concentrations, particularly the sulfide species, reach levels high enough to saturate in sulfide. In a magma, that might be 1,000 or 2,000 parts per million. Now, there are elements like copper and silver, which are rare, but if you have sulfides present, they control the behavior of copper and silver. So let's talk about how we're going to model the evolution of two elements. One is the essential structural element, and I'm going to call that E. Its concentration. I usually use C, but I'm going to use E to describe concentration of zirconium or sulfur in the accessory phase, the essential structural element in the phase. And when we look at how these elements behave, we always have to consider mass balance. So the essential structural element concentration in the bulk system, I'm going to call E0, and that, of course, is equal to the essential elements in the melt times the melt fraction, which is F, plus the essential structural element concentration in the solids times the fraction of solids, which of course is 1 minus F. Okay. So we're going to separate things with the melt here and the solid, and F is the melt weight fraction relative to the total mass of the system. Okay. Now, ES, the amount of or the concentration in the solid fraction, can be broken apart into two components. One is the essential structural element concentration in the accessory phase, which you can get from stoichiometry, meaning that if you just take a look at the formula for zircon, zirconium silica 04, you should be able to calculate the concentration of zirconium in it because it's all zirconium in that particular site. Same thing with sulfides. You know how much sulfur is in a sulfide. And that's going to be multiplied by little f, and little f is a fraction or the accessory phase fraction relative to the mass of the solids, not to the mass of the whole system. Okay, so that's critical. And that then becomes 1 minus f, which is everything else besides the accessory phase times the concentration of the essential structural element, like sulfur, in all the other phases, which we'll call other. Okay? And typically, when we're thinking about these essential structural elements, their concentrations in all the other phases besides the accessory mineral or phase, you can pretty much consider them to be zero. Like sulfur doesn't go into any of the silicate minerals. Zirconium does, but it's in trace amounts. But it's such a large constituent in zircon that we can ignore this quantity right here. That goes to zero. So the conditions we want to look at are the case when there the two end members, when there is no accessory phase. That would be the case where the system is undersaturated in that essential structure element. So for sulfur, for example, sulfur contents are not high enough to saturate sulfides, so there are no sulfides. In that case, case 1, we'll call that the undersaturated state. Fc of the accessory phase equals 0. Okay? This F accessory is the same thing as my F up there, just so you know. And if I make that 0, then it turns out the first equation up here, the only term that matters is the first one, right? E0 is equal to EMF. And so this leads to that the concentration of the element, essential structure element in the melt is equal to 1 over F, okay? And so, again, taking sulfur, for example, if there's no sulfide present, then sulfide concentration will scale exactly with 1 over F, simply because sulfide or sulfur does not fit into any of the silicate phases, perfectly incompatible. This would be the same solution you'd get when you did the batch melting models for a perfectly incompatible element, or D equals 0. So it's very simple. The other case, or end member, would be when you're saturated. And you don't have to be saturated with much. As long as it's saturated, it's saturated. And that's the case when F is not 0, finite. Okay. In that case, we have to consider what saturation actually means. When it is, a sulfide phase is saturated, the composition or the concentration of that element, essential structure element like sulfur in the melt, is only controlled by the solubility. For sulfur, we might call that SCSS, sulfur capacity at sulfide saturation, something like that. Maybe sulfur concentration at sulfide solubility. Maybe that's the right term for that. So that would mean that at saturation, that EM is defined to be what I'll call EMS. Okay, and this term, or that concentration, must ultimately be constrained by experiments, and it will of course change as a function of temperature and pressure and melt composition, but I'm going to assume here that it's constant just to be simple. So let's draw what this might look like. If I were to plot Cm here, okay, this is Cm over, Em, okay, over E0, and this is F, okay? And we're gonna track the evolution of the melt. This would be at 100%. Okay. And we'll draw this up. This is 1 right here. This is 0% melt. And at 100% melt, of course, Em over E0 is equal to 1. And we're going to assume that initially the system is undersaturated in, say, sulfur, sulfide. And so if you crystallize this melt or decrease the melt fraction, then you will keep going up by 1 over F. Okay, that would be the behavior. Move this over here. Okay. But eventually, you're going to hit a point where you hit saturation. And if we call saturation this line right here, I'm going to call that my saturation line be this is M S, okay? That's the saturation. That pen is not working very well. Then what that would mean is that once you hit saturation, and from that point on, the melt concentration composition must follow that at saturation. Okay, so here it's saturated, here it's undersaturated. Okay. Okay. Now the interesting thing is in this saturated state, if we plug in or substitute these equations to combine them together, what you end up with is a equation describing the concentration of the essential structural element in the solid, average solid, would be this, Em S F 1 minus F, okay? And this, of course, would be EACC times the little f, okay? And we can consider the case when at F equals 0, which is no melt present, this is completely solid, then little f, the amount of the accessory phase would be ES over E there, okay? So it's the bulk amount of, say, sulfur in the system, and then divide by how much sulfur is in the accessory phase or sulfide, right? We can also consider the case that's this. The case when you're going to exhaust, this would be F at 0, F to when it makes it 0, when you subtract out all of the accessory phase. Plug those plug the 0 in for little f, and you'll get E0, right, over ESM. Okay, so how does this work? Let's make a plot here, same plot here with F. And what I'm going to do here is show you the solid part, E0, okay? So when F equals 0, it'll have a finite amount of the essential structural element. We're going to call this level right here 1, okay? And now I'm going to melt the rock instead of crystallize it. So let's consider a peridotite with, say, 200 ppm sulfur in it, in which case it has probably about 0.06 weight percent sulfide. And it's saturated in sulfide, the melt, from the very beginning. So the first melt you generate might have 2000 ppm sulfur because that's the solubility of sulfur at sulfide saturation. But once you melt, that means some of the sulfur from the sulfide has to get into the melt to maintain it at 2000 ppm. And the way you do that is you actually consume the sulfide. And eventually you consume all the sulfides, at which point you become undersaturated. And then your melt follows the case where sulfur is perfectly incompatible. So if we look at the solids, then this is the case, what you'll see, okay? That the amount of sulfur in my residual solids starts off at 1, and it'll decline, in this case, linearly, because I assume that ESM is constant. But it'll go to 0, and this point right here should correspond to this point right there, okay? And if I go back to this equation down here, let's do that right here. F right here, this one, is the melt fraction at which your accessory mineral phase is completely exhausted. And you can see here that it depends on two quantities, how much you start with and the solubility in the melt. If you start with a lot, then of course, say you start with a lot up here, then of course you would exhaust the much later F. If you had a higher solubility, but started at the same amount, then that would just have a steeper slope right there, okay? See, that would be a steeper slope. So you can model that. So it turns out it's all relatively simple. So now what we're going to do, I think I have a nice box around all of this. I want to model the behavior of a trace element, C, that goes into the accessory phase, but not into all the other phases. We're going to assume it's partitioned so strongly into the accessory phase that the other phases don't really matter. And if you recall from our batch melting models, the equation for batch melting is Cm over C0 is equal to 1 over D plus F 1 minus D, okay? F, again, is the melt fraction. D is the partition coefficient, right, where D is equals to the concentration in the solid divided by concentration in the melt, okay? But when you have an accessory phase, this equation would be looking just a little bit different. And the way you would derive it is to go back to your simple mass balance there. And it would be Cm times the melt fraction plus D, I'm going to do this, DAC, I'll write it out and then explain later. 1 minus F. Okay, so the first term is the total amount of that element in the melt. And the second term is that all in the solids, and it's assuming that only the accessory phase matters. So 1 minus F is essentially the mass of the solids. FACC, that's the same F as all the little f's I have here, is the mass fraction of my accessory phase relative to the solids. That's why I multiply little f by 1 minus F. And then this term right here with the D times the C, well, that's actually just the concentration of my trace elements in my accessory phase, but it's related to the concentration in the melt by this partition coefficient D, okay? And I pulled it out there, that's why it looks like that. You can rearrange all this, and then you will get an equation like this. Cm C0 is equal to 1 over F plus DACC E0, my essential structure element, minus EM at saturation, F, okay, over E of my accessory phase, okay? And what I had done here is I have rearranged all of this, but the little f here is what links me back to this area, the essential structural element. This right here, right, tells me what little f is. That's this f here and this f here are the same. By plugging this into here, we get this equation here, which very much looks like the batch melting equation or crystallization equation, except for the fact that now we account for accessory phase. Okay. So we can look at Cm, C0 over F, and once again, I'm going to call this 1 right here. When you're not saturated, then my element should behave as a perfectly incompatible element. It goes like that. Obviously, you can add the complexity where all the non-accessory minerals, all the other phases do contain some of this element. So it might be less than the 1 over F relationship, but I'm not going to do that for simplicity. But once you saturate, like here, then that means that the partitioning of this element into the accessory phase becomes important. And so you're going to have the curve look like this. So let's say if you're fractionally crystallizing, then first you start off undersaturated, undersaturated, undersaturated. So undersaturated here, You hit saturation, sulfide kicks in, then that suddenly causes efficient scavenging of, say, copper. If this was the element of interest, um, down here, because copper starts to become compatible. If D of accessory phase is very high. And if I were to plot, well, that's not what I wanted. Here, F CS over C0, then what we would see is that the copper would go down. And the copper would start off at some value dictated by this mass balance. And once you get rid of all the sulfide, there's no copper left. But when sulfide is present, then copper behaves as a compatible element, and the melts are going to be depleted in copper. So if you were melting a peridotite, so going from here to here, increasing melting degree, you could, the copper is held back until you consume all of the sulfide right here, at which point copper is liberated, and then it behaves like an incompatible element, and it goes down. Okay. Now, the effect of differing partition coefficients for copper in my accessory phase, like sulfide, well, that's going to basically change the slope of these lines of copper when sulfide is present. Okay, I hope that helps. I had a little trouble with writing here because I have a new pen, but hopefully this works for you.